welcome back to the second part of parameterized algorithms. Here we're going to talk about iterative compression, which is a really cool and powerful technique for coming up with FPT algorithms for certain kinds of problems. We are going to be talking about vertex cover to begin with as a warm-up example. So it's not the best known algorithm that we're going to see for vertex cover. In fact, what we will come up with will simply match the running time that we have already seen using the branching algorithm in the previous part. So you might wonder what we have achieved, but the goal of this discussion is not to improve the running time that we already know for vertex cover. The goal is to understand the framework of iterative compression and how it works. And once we are comfortable with that, we can go on to use it for other problems. So in the next part, we'll talk about how iterative compression can be used to solve feedback vertex set. And there we will have more ideas and more moving parts. So think of this as a warm-up discussion leading up to other examples, and hopefully by the time you're done with both of these parts, you'll be ready to apply iterative compression to other kinds of problems as well. Okay, all right, so with all that said, let's get started here. So recall that in the vertex cover problem, we have a graph and a budget k, which we think of as the parameter now because we're talking about the standard parameter, and we want to know if there is a vertex cover of size at most k. Recall that a vertex cover is simply a subset of vertices which intersects every edge at least once. Okay, so that's the setting. And in iterative compression, what we do is we step back a little bit and ask ourselves if we can solve our problem if we already have a solution. Now, that sounds funny because why would you solve a problem if you already know the solution? But the interesting thing here is that the solution is not quite what we want, but it's close to what we want in the following sense. So the compression problem for vertex cover is the following. It's the same as before, except on top of the usual input, which is g and k, we also have T, which is a subset of vertices that already form a vertex cover, but notice that its size is T plus 1. So its size is K plus 1. So that's one more than what we wanted. It feels like it's so close. It would be what you might call a plus 1 approximation. But remember that we're not trying to solve the approximation question here. We want to know if there is a vertex cover of size at most K or not. So in some sense, the solution T does not immediately solve our problem, but the question is it useful? Can we use it to find a solution of the sort that we actually want? So it turns out that having access to a solution that's almost there of size K plus 1 is actually something that anchors the input in such a way that you can actually use it to effectively find a smaller sized solution. So we're going to come back to the compression problem. If you want, you can pause here and think about how would you solve this. Notice that the set T actually gives you a partition of the vertex set into one small part which has k plus 1 vertices and a large part which is an independent set. So this is already access to a lot of structure, and the question is, can you exploit this structure to look for your solution of size at most k, or conclude that there is no vertex cover of size at most k? So that's the question with compression. But okay, you could also be wondering about where does the solution of size k plus 1 come from? Is that something that we can easily get a hold of? Because we already know that you can get solutions of size at most 2k easily using, for example, the matching algorithm. You can find a maximal matching and pick up both endpoints. And if when you do that, you have picked up more than 2k vertices, you can already say no, because that means that we have a matching of size more than k. So there's no way this graph has a vertex cover of size at most k. So that's the easy case. You find a maximal matching, it turns out to be too large, you say no. Otherwise, you have a set of not k plus 1 but 2k vertices which just happen to form a vertex cover. And you could ask yourself the compression question in the light of this approximate solution. You could say, well, we have this starting point, we have a solution of size at most 2k, and can we stare at this and somehow use it to come up with a search for a vertex cover of size at most k that runs in FPT time? So that's a nice question to think about as well. But the way I've phrased the compression problem here is whether this is the more traditional framing where you have a solution that's even more tantalizingly close to what you want. It's off by just one, and the question is, can you compress this into a smaller solution? And what I'm going to do is set the compression problem aside for a second. We'll come back to it, but what I want to talk about first is how does access to a compression algorithm, even if you had one, how does it help you solve the whole problem? Where does the solution of size k plus 1 come from? And why is it useful to solve the compression problem? Because once we talk about that, hopefully we are motivated to come back and solve the compression problem because we know that it's going to be useful. So we're going to talk about a fairly generic sort of a framework, and this is the iteration in iterative compression. So for now, let's assume that we have some sort of an algorithm that can actually solve the compression variant of the problem. And you could step back for a minute and think of this in more general terms. So for any optimization problem, especially problems that are subset based, but you could also think of it for other kinds of problems as well. The basic question we're asking is, well, suppose we have an algorithm that can solve a compression variant of the problem, and usually the compression variant is you're given the problem as it originally is stated, plus you're given something more, and the something more is supposed to help you with finding additional structure in the input instance. So typically the something more is a solution that's a little bit worse than what you're looking for, as we just saw for vertex cover compression, but it could be all kinds of other things as well. And now the question is, well, if we knew how to solve this version where we have some additional help, can we use that algorithm to solve the base problem, right? And the answer to this, of course, depends on various things. It depends on the problem itself. It depends on what the compression variant looks like and so on. So let's walk through how we can use the compression algorithm to solve the base problem for vertex cover in the way that we've stated the compression problem. Remember that we just have access to an algorithm that can take solutions of size k plus 1 and compress them to solutions of size at most k if they exist. Otherwise, we say no, right? That's what we have access to. We have an algorithm that can do this. And now what we want to do, of course, is to solve the original problem where we simply have a graph G and we have our budget k, and we're simply looking for a vertex cover of size at most k. So how do we bring the compression algorithm into this picture? Well, here's what I'm going to do. I'm going to cut off k plus 2 of my favorite vertices from the graph. So let me look at a subgraph H where H has k plus 2 vertices only, right? I'm going to forget about the rest of the graph for the moment. So I'm going to focus all my attention on this subgraph here. And you might be wondering, well, how do we choose the subgraph? Is this a specially chosen subgraph? But it's not really. You can pick any k plus 2 vertices that you like to begin with, and this is going to be the first thing that we focus on. Now notice that because H only has k plus 2 vertices, it has a trivial vertex cover of size k plus 1. You can pick any k plus 1 vertices that you like here, and that would be a valid vertex cover of size k plus 1 for H, because you would leave out only one vertex, right? And that's just by definition vacuously an independent set, and the rest of it is a vertex cover of size k plus 1. Now this whole thing here we can feed to the compression routine. So we send H and this trivial k plus 1 size solution to the vertex cover compression algorithm. And what does the compression algorithm do? Well, it takes an instance of vertex cover as input, and it also takes a solution whose size is 1 larger than the budget. So that's exactly what we have here. We have specified a budget of k, and we have a solution of size k plus 1, and the compression routine can now figure out if this solution can be, maybe not using this solution as input, it figures out if there is some solution of size k or not, right? Now if the compression routine says no, there is no solution of size at most k for h, then what can you say? Pause here and think about this for a second. Okay, we have a subgraph of G where there is no vertex cover of size at most k. What does this tell us about G? Well, if you think about it for a while, you'll probably reach the conclusion that G also does not have a vertex cover of size at most k, because vertex cover is a hereditary property. So suppose G did have some vertex cover of size at most k, right? So suppose there was some set of at most k vertices that formed a vertex cover of G, then if you look at the intersection of those at most k vertices with H, just project the solution on H, you get a subset of at most k vertices which must have formed a vertex cover for H as well, because if it didn't and there was an edge outside, then this set is not a vertex cover for G either, right? So if G had a vertex cover of size at most k, then H would also have a vertex cover of size at most k. Now, the fact that H does not have a vertex cover of size at most k, as reported by the compression algorithm, therefore implies that G also does not have a vertex cover of size at most k. This is just the contrapositive. So G has a vertex cover of size at most k implies that H, which is any subgraph of G, also has a vertex cover of size at most k. So that's P implies Q. The contrapositive would be that not Q implies not P. That means that if H has no vertex cover of size at most k, then G also does not have a vertex cover of size at most k. So if the compression routine says no, we can also say no, and we have totally resolved the instance at this point, right? But if the vertex cover compression algorithm comes back and says, yes, here is a vertex cover of size at most k, what do we do then? Well, in that case, let's actually look at the solution that the vertex cover compression algorithm came up with. So this is now some set of, at most k vertices that forms a vertex cover, and now there's going to be at least 2 vertices outside, maybe more, right? So this is the solution reported by the vertex cover compression algorithm. And remember that this is only solved for H. This has given us a solution of size at most k for this k plus 2 sized subgraph of G. But of course, we're interested in all of G, so we have to, from here, try and see if we can incorporate more from G and continue our journey. So what we're going to do is basically expand the purview of H to include one more vertex from G. So now we are upgrading H from being a k plus 2 size subset to a k plus 3 sized subset. And we're going to bring in one more vertex, and I'm going to add this vertex to the vertex cover that we got from the compression routine. So from the compression routine, we already had k vertices. Now I bring in one more vertex and I add it here. So all the all the edges that this new vertex was potentially bringing in to the graph are automatically covered because this new vertex has been incorporated into my vertex cover. So the old vertex cover, which was the output of the compression algorithm, plus the new vertex that we have brought in, is now a vertex cover of size k plus 1 again for this new H, which now has not k plus 2 but k plus 3 vertices, right? And now you probably see where this is going. We now again have a situation where we have an instance of vertex cover. We have a solution whose size is one more than the budget that we are working with. And we have something that is suitable for feeding to the compression algorithm. So we do that, and it's essentially the same story now. If the compression algorithm says no, we can say no. But if the compression algorithm manages to find a solution of size at most k, then we hold on to that solution and we bring in one more vertex of the graph. And we keep doing this until we have exhausted the entire graph. So this is why this is called iteration, because you're iteratively applying the compression algorithm over the whole graph. So here's another way of looking at it, a different schematic, which shows you a snapshot of a typical intermediate iteration. So suppose we're doing the ith iteration. By now we have processed some I minus 1 vertices. The compression algorithm has worked so far. It's given us a thumbs up every time. It's given us solution of size at most k every time that we have run it. So let's say the last solution of size at most k that we saw with I minus 1 vertices, let me call it Si minus 1. And now in this step of iteration, what we are going to do is we are going to combine Si minus 1 with the newly brought in vertex Vi to obtain a new solution of size k plus 1, and we feed that to the compression algorithm. Now, what we already know is that if the compression algorithm says no, then we can also say no, and our algorithm is actually done at this point. There's nothing more to be done. On the other hand, if the compression algorithm says yes, then there is some hope. So we make progress by saying, okay, let's look at the solution returned by the compression algorithm. Let me call that Si. And now we have basically processed these I vertices, and it's time to bring the I plus 1th vertex into the fold. So now we use Si union Vi plus 1 as the next thing that gets fed into the compression routine, and you go on and on. If you reach the very end successfully, that means that you have found a vertex cover of size at most k. If you stop at some intermediate stage because the compression algorithm reported a negative answer, that means that your graph does not have a vertex cover of size at most k to begin with. Okay, so that's how iteration works in iterative compression. And now we appreciate that if we knew how to solve compression, if we knew how to solve vertex cover compression in whatever time, then we can solve all of vertex cover in time roughly n minus k times whatever time we needed to solve compression, because we are basically repeating the compression routine n minus k times, and you might add another polynomial overhead for the work involved in picking up a vertex, adding it to the vertex cover, and things like that, right? You can probably do this more efficiently, but this is just a valid upper bound on the overall running time. Basically, the running time of the compression routine with a polynomial overhead solves the entire vertex cover problem, right? So that's what we have with iterative compression. And now let's go on and talk about how to solve the compression problem, because that's the only thing that remains. If we can solve compression, then we basically have this whole thing down, right? Okay. So recall that for the compression problem, what's going on is that we have a k plus 1 size solution given to us as a part of the input, and we want to know if there is a solution of size at most k. What this means for vertex cover is that we have some k plus 1 vertices, which we called t, which we can set aside so that the rest of the graph forms an independent set, because t covers all of the edges. So what's outside is a set of n minus k minus 1 vertices, which have no edges whatsoever, right? And one way to think about our solution of size at most k, if it exists, the one that we are looking for, is to think about where does the solution overlap with t, right? We don't know anything about this solution, but what we can do is go over all possible ways in which the thing that we are looking for overlaps with the thing that we have. And notice that that's doable because t is small, okay? Because it would also be valid to say, well, the vertex cover that we're looking for, where does it intersect with v minus t, right? But that would be a really expensive guess, because you would be looking at all possible subsets of size at most k of v minus t, which is a set of size n minus k minus 1. So that's going to go out of hand. You're going to again start seeing n choose k kind of running times, which you want to avoid. Our goal is to come up with a FPT algorithm, right? So instead, let's think about, where does our solution overlap with t? Basically, was t right about some vertices, right? So there's a solution of size, let's say we're looking for a solution S of size at most k, and we want to know what does S intersection t look like. Okay, does t coincide with the thing that we are looking for in some vertices? And we don't know, so we are going to guess. We're going to try all possible subsets of t that actually are candidates for S intersection T, right? So let's say this is a typical guess. We could, this is one partition of T into two parts. Here we are saying these guys here, T was right about them. So this is our guess for S intersection T. And this is therefore everything that is in T but not in S, right? And now the next thing to do is to see if we can try to validate this guess, right? Is there a vertex covered S which picks up precisely these vertices from T and has size at most K? Well, how do we think about this? Well, we know that the guys that we have picked are doing their job and they're covering the edges that they used to cover as they did in T. But now let's talk about T minus S. These are the vertices that we are going to throw away from T. And these are the vertices that we potentially have to compensate for, because right now S intersection T is probably not a vertex cover on its own right, because if it was, that's the end of the story, right? We have found a smaller vertex cover immediately because there is apparently a subset of T that works just as well as T. Then of course we would immediately be done. But typically that's not going to be the case. So these vertices in T minus S were presumably in T for a reason. They were covering some edges, and now we need to extend S intersection T to be able to cover those same edges, but without using the vertices of T minus S, because we are committed to not picking them, right? So where are these edges that are incident on T minus S? Let's maybe zoom in a little bit on T minus S. Now these vertices would of course be having edges in, for example, V minus T. Those were the edges that they were originally covering. They may have edges with vertices in S intersection T. That's also fair game. And there could potentially be edges between vertices of T minus S. But notice that if there is an edge between two vertices of T minus S, then our guess S is just a bad guess, right? Because we're saying that we're not going to pick any of these vertices in our vertex covered S. And among the vertices that we have chosen not to pick, two of them happen to have an edge between them. So this edge out here basically is completely hopeless, right? There's no way that we can cover this edge having decided to pick neither of its endpoints, right? So if your choice of S intersection T is such that there is an edge in T minus S, then you can immediately discard this guess, right? This is not going to work. This set here cannot be extended to a vertex cover given our decision to not pick anything from T minus S. So if you see an edge in T minus S, that's an easy case. Just chuck this guess and move on to the next one, okay? But suppose that for the sake of argument, T minus S is a valid independent set. The edges that vertices in T minus S have with vertices in S intersection T, these are good edges. We don't have to worry about them because S intersection T already has our back. These edges are covered by our current choice of vertex cover vertices. So these edges we don't have to worry about at all. On the other hand, the vertices in V minus T, the independent set vertices that have adjacencies with vertices in T minus S, these are the ones that we need to work on and make sure that these edges are still covered. And one way to basically cover these edges is to say that, well, we've decided not to pick these endpoints, so we'll have to pick the endpoints that are in V minus T. So in other words, look for every vertex that is a neighbor of somebody in T minus S, right, in V minus T, okay? So essentially look at the neighborhood of T minus S. We have decided that there are no neighbors within T minus S. So the neighbors are either in S intersection T or V minus T. So look for the neighbors in V minus T. And we know that these vertices in V minus T that have edges into T minus S, they're now forced into S because these edges have to be covered. We've decided not to cover them from the other side. So they have to be covered from the V minus T side. So essentially what we are doing is we are saying, well, look at T minus S and look at its neighborhood in V minus T. Now, if this neighborhood is smaller than the size of T minus S, then we are in luck because essentially what we are doing is swapping out these two sets. We are saying from t, get rid of t minus s, and from v minus t, pick up the neighborhood of t minus s. And this combined with s intersection t is our new vertex cover. So basically, if we gain less than we lose, that means in the net calculation, we have lost at least one vertex, right? So in particular, let's say that there are three vertices here that altogether have only two neighbors in b minus t, right? Then that's an effective swap. That's a good swap for us because we're losing three vertices and gaining two. So that's a net loss of one vertex. So the size of our vertex cover has actually gone down. On the other hand, if these three vertices altogether have 4 or 5 neighbors, then we are swapping out three vertices for 3 or more vertices. That's not a good situation because then we are back to square one. We have a vertex cover of size k plus 1 or worse, even larger. So those are not good swaps for us, right? So the idea is to check if t minus s has a neighborhood that's smaller than itself. If it does, then we are in business. This is a good guess. We have actually found the vertex cover that we are looking for, a vertex cover whose size is k or less, and we can stop here. Otherwise, we move on to the next guess, and we're moving on typically for one of two reasons. Either because t minus s already had an edge inside it, so this is not even feasible to extend s to a vertex cover, or the problem would be that we could extend it, but the extension is too expensive. So we end up with, again, k plus 1 vertices or maybe even more. So that would be another reason to discard a guess. Okay. So what's the compression algorithm? It's going to basically say for all, let's say, x subset of t, and we're only looking at proper subsets because it doesn't make sense to pick all of t. But for all x subset of t, we are going to check, first of all, so x is our guess for the vertices that are going to stay. So we are going to check if t minus x is an independent set. And if it's not, we already discard this guess. But if it is, then we want to check if the neighborhood of t minus x in v minus t, if this is smaller than t minus x. Okay, so if both of these checks pass, that is t minus x is independent and it has a smaller neighborhood in v minus t than its own size, then we know that we can combine x with the neighborhood of t minus x and v minus t, and we get away with a smaller vertex cover than the one we started out with. Okay, so then we are in business. But if either one of these checks fail, then we move on to the next guess, and if none of the guesses work, then we can say no. The reason for that is that we've been completely comprehensive. Any vertex cover of size at most k, if it exists, must intersect with t somewhere in some fashion, even if it's just the empty set. But we've gone over all possibilities, right? And if none of them worked out, then we know that there is in fact no vertex cover of size at most k. So the correctness of the algorithm just follows from the comprehensiveness of the search, that we really have tried everything. And for each of these attempts, we have done exactly what is needed to be done to check if the guess is valid, if there's a valid extension or not, right? So if you think about it a bit, you can convert everything that I said into a formal proof of correctness for the compression algorithm that we have just proposed. The last thing I'd want to talk about is the running time of this compression routine. So notice that the bulk of it is in this outer for loop. So all of these guesses that we are making, that's roughly 2 raised to k plus 1. If you want to be precise, you'd probably say -1 because we don't actually include t in our collection of guesses. But asymptotically, this is a order 2 to the k sort of a running time. That's the dominant factor. Both of these checks take polynomial time. It's just a matter of looking up your adjacency matrix or adjacency list, however you've chosen to store the graph. You're simply checking for the presence of certain edges and counting off certain neighbors. So all of that is simply a polynomial overhead. So the overall running time is basically bounded by 2 raised to k for the compression routine. And then there is a polynomial overhead, both within the compression routine as well as when we perform the iteration. So the compression routine gets plugged into another sort of outer for loop, which is the iteration, but that's only polynomially many iterations. So essentially, this is a 2 to the k algorithm, and that's it. That's our first encounter with an iterative compression based algorithm. So next time we will talk about the same technique as applied to a different problem. So you're going to talk about solving feedback vertex set using iterative compression. So that's what's up next, and I'll see you then. Thanks so much.